Tomorrow, you need a protractor and ruler because we're starting vectors tomorrow, okay? Protractor ruler, you don't have to have like the gold-plated one. You can probably rummage around the house and find them. If not, Target and Walmart have them. Okay. Also, if you're taking this class for dual credit, there's an absolute set-in-stone deadline of this Friday to be enrolled, okay? Don't come to me next week and go, well, hey, I changed my mind. I don't know, okay? This isn't like a Mays deadline. This is a college deadline, which means that's set in stone. If you have any questions about that process, do not ask me. Not my bat and ball, okay? I can give you the email address of the people to talk to. They're great about responding to emails in a very timely manner. But if you have a question about the process, we'll transfer that type of thing. Not my bat and ball, okay? Not my bat and ball. But I can get you in touch with people that can answer that question. So those are the two big deadlines. Okay, so on the lab that you're going to do today, hold on, I gotta get my card. Hold on. So this is kind of like a lab final, okay? It's a practical of what you all have learned so far. So we're going to take the cart and we're going to give it a push, and it's going to hit a wall, and then it's going to bounce back, okay? That's it. Push it, boom, hits the wall, bounces back. And what we're going to try and do is analyze that motion to draw position time graphs and velocity time graphs to describe what is taking place in the lab. So, to start off, we're going to assume that it's already moving when we start the analysis. So guideline number 1, do not include the push, okay? So you're already going to push it. It's not, okay, so do not start your velocity time graph at 0, 0. It's already moving. And we're going to assume that the direction towards the wall was positive. The direction coming back from the wall is a negative value. Okay? Positive, negative. Now, so to start this off, imagine this. I'm going to give the cart a push, okay? And it's going to roll along. And as the cart rolls, it slows down a little bit. Okay, because there's a little bit of friction. Don't try and do the lab like this. It's not going to end well. Okay, make sure you do the wheel side down. So you're going to give it a push. It's going to roll along, and then we're going to stop it very quickly. Okay, all we're going to do is stop it. So imagine this. It's rolling. We stop it. So what would the position time graph look like for a cart that's rolling and then suddenly stopped? Deacon.
It would start at some value and curve down, and at the very
No. Okay. We're going to make this the reference point. This is going to be 0, where I let go of it. And we're going to have positive positions going this way.
it's going to travel to the right, and as it reaches the stopping point, it's going to curve down very quickly.
So this is a position time graph, right?
Yes.
So you're going to say it's going to go like this and that.
No. It's just going to curve up and it's going to stay there.
Why?
Because when it stops, it doesn't travel back to the reference point.
Okay. So maybe something like this.
Yep.
Ish. Okay. Andrew, why is this curve kind of flattening out a little bit as it rolls?
The friction.
Yeah, there's a little bit of friction, okay? And we're going to spend a lot of time talking about friction. Friction always acts in the opposite direction of motion. Friction will never make you go faster, okay? So friction always impedes your motion. So we're going to eventually be talking about two different types of mafia. The frictional mafia and the gravity mafia, okay? So the friction mafia is always trying to slow you down. Friction mafia is never going to make you go faster. Friction mafia will always slow you down, okay? So, but because we're doing the wheel sides, the friction mafia is there, but it's not that important, okay? There's a little bit of friction, not a lot. But it's going to roll along, and then bam, it's going to stop. So look, why does that plateau out when I stop it?
Because you're at a time, like time is still going on, but it's not changing position at all.
Beautiful. And what's the slope of a horizontal line on a position time graph represent?
The object's at rest.
Yeah, it's at rest, because the slope is 0, therefore it's at rest. Okay? Now, what would the velocity time graph look like? Keeping in mind it's already moving. Chuck,
It would slow down.
got a little, that's a little vague. Where would it
Positive.
start? Where would it start? Would it start here at 0 or at some positive velocity up here?
Some positive velocity.
It's going to start at some positive velocity. Cool. Then what's it going to do?
Go down till it touches the time axis.
Same slope the entire time, something like this?
Yeah.
Everybody cool with that? No, don't be. Do not be cool with that. Do not be cool with Chuck. Because here's the reason why. Because what does a straight sloping line on a velocity time graph give you?
Constant
Chuck?
acceleration.
Uniform acceleration. F equals ma, right? So if Chuck's line is right, that means I'm applying the same force to the cart the entire time. Was the same force applied to the cart the entire time?
No.
Chuck, when was the maximum force applied to the cart?
When it stopped?
Yeah, because initially it was slowing down just a little bit and then bam, stopped. So the dashed line's bad. So let's start with this. Leave me stopping it out of the story. You got one of two choices. Either the line is going to have a shallow slope up or a shallow slope down. Mitchell, which one? Up or down?
Down.
Down. Because it's slowing down a little bit. Okay? Now, when it's slowing down, and I realize this is a relative term, but when it's slowing down, I'm going to have just a little bit of negative acceleration because I got a little bit of influence from the frictional mafia. Okay? Not a lot, just a little. So the cart's rolling along, slowing down a little bit, not much. Okay? Minding its own business. And then all of a sudden, bam! So Chuck, what does bam look like on the
Straight
graph?
down.
Huh?
Straight down to 0.
Well, pretty straight, or pretty steep anyway,
Pretty.
right? Something like this, perhaps? Which line is the bigger acceleration? The shallow line or the bigger line, or the steeper line, Chuck?
Steeper line.
That's big acceleration, okay? The only way I can create big acceleration is if I have a big force. What created the force? Me stopping, okay? Try to stop, right? To make it stop. If I didn't stop it, what would the graph have done? Then your line would have been right. Because then it would have rolled and rolled and rolled, and it just would have stopped. Okay? Is it slowing down as it rolls?
Yes.
I can put a little down arrow. Oh, it's slowing down, right? Does it slow down when I hit it?
Yes.
Slows down rapidly, right? If you were to find that area, what would that represent?
Displacement.
How far it goes from when I let go of it until
You stop it.
stop. Cool. Got that. Now we're going to change up the game. Now we're going to have a roll hit my hand and bounce back. Okay? So the function of the plunger is to store what we call potential energy. So we're going to spend a lot of time talking about energy. In the broad classifications, there's two types of energy. There's kinetic energy, which comes from the Greek word kinesis, which means motion. And then you have potential energy, which is stored energy. So the two broad classifications of potential energy are energy stored in a spring, like when you push this in, or you can have gravitational potential energy when you lift something up and let it fall. Okay? So energy in a spring, gravitational potential energy. In both situations, I have to do a concept called work. I have to exert a force over a distance. Either I push in the spring or I lift it up. I have to do work. I have to exert a force over a distance. So, one of the great axioms of science is that Mother Nature hates potential energy. At some point, somebody posted a story on Snapchat, Instagram, something. Okay? Mother Nature and potential energy don't like each other. Mother Nature and kinetic energy, hashtag best friends. Okay? They like each other. Potential energy in Mother Nature, not so much. And here's the reason why. I'm going to take this plunger and I'm going to push it down. I just stored potential energy. If Mother Nature liked potential energy, what would happen when I would take my finger off?
It would stay there.
It would stay there. Because Mother Nature goes, potential energy and I were besties. Okay? So what would happen? When I do this, Mother Nature goes, no, I like kinetic energy. Same thing is true, and the universe would work completely differently. If I held this up and stored gravitational potential energy, and Mother Nature liked gravitational potential energy, and I let go of it, what would it do? It would just stay there. Because Mother Nature goes, potential energy, we're tight. Okay? And it would just stay there. But no, what does Mother Nature like? Kinetic energy. Okay? Same idea. Mother Nature doesn't like potential energy. Mother Nature likes kinetic energy. So, here's the story. So I'm going to roll this in. It's going to hit the plunger. It's going to change direction. And it's going to come back. Mr. Hanna, does the cart change direction when it hits my hand?
Yeah.
What three things does it have to do to change direction?
Slow down, stop, speed up.
Does that happen in a relatively short amount of time or over a long period of time?
Sure.
Sure, okay? It's rolling along, bam,
Yeah.
really short amount of time. So here's the question. What would the position time graph look like for this rolling in, hitting, and bouncing back? Deacon, what we got this action going on the table. What does that look like?
It's gonna start at 0,
Okay?
it's gonna travel up, and it's gonna curve to a point, and then it's
Okay.
gonna curve back down.
So when it curves back down, is it going to be a curve like this? Or the dashed line curve? Mr. Etheridge. Top lip, bottom lip.
Bottom lip.
You say that with no
I
confidence.
don't have any confidence.
You should have confidence. It's the right answer.
Okay.
Why is it the right answer?
Because it slows down over time.
Ah! What would the upper dash line show?
Speed up over time.
That would show that it was speeding up as it rolled back towards my hand, which would be cool, but it's a violation of conservation laws. Okay? So it's going to be the bottom line. Okay? Now, here's the question. What's happening to the plunger at that very peak of that point? Where's the plunger? What's it doing?
It's all the way back.
Completely compressed. Because you've taken all of that kinetic energy and you changed it into potential energy. But Mother Nature doesn't like that, so Mother Nature goes, we're going back to kinetic. Okay? In a very short amount of time. So this is where it meets Mr. Hanna's criteria. So it's going to slow down, stop, and then very rapidly it's going to speed back up, but it's only going to speed up as long as the plunger expands. Because as soon as that plunger stops expanding, what's it going to begin to do? Slow down. Okay? Cool with that? Got that. So what's the velocity time graph going to look like? Connor M., will the velocity time graph start up at some positive value?
Or it going down from the stop?
Yeah, so it's going to go from here, doink, back.
No,
Yep. Because we're not going to include the push.
then yeah.
Then, so it's going to start here. So Connor M., as it rolls, it's going to slow down a little bit. So how can I show that slowing down just a little bit on that velocity time graph?
Just a straight line to the time.
Not a straight line. It's just going to slow down just a little bit. Maybe something like this. And here's, I'm just going to have a little bit of a negative slope because it's slowing down just a little bit. Okay? Because it's just a little bit of friction. Conrad, last question. Plunger's going to hit. What's that graph going to do when the plunger hits?
Switch directions.
It will eventually, but what are the three things it has to do to change direction?
Speed up, stop, slow down,
They'll reverse that. First thing it has to do is
slow down.
slow down. So how can I show this slowing down very rapidly?
Just a straight.
Yeah, or maybe a little bit of a slope to it. Okay? So it's going to come down like this. Mr. Hanna, does that fulfill your first criteria?
Yeah.
Because what's it doing?
Just slowing down.
Slowing down. Connor M., what's the velocity at that point?
0.
0, because now we've stopped. Now, how are we going to show it speeding back up again? It's going to do one of two things. It's either going to bounce back up and it's going to come up like this, or it's going to continue down like that. Ms. Dowser, what's it going to do? Why? Why want to go back up?
Negative velocity when you're going back.
What would it mean if the line came back up?
Positive velocity, it'd be going the same direction.
Yeah, which would not end well for my hand, okay? Because if you brought that line back up, I'm going to stop it, but then it's going to speed up through my hand, okay? Like what happened to your hand? Oh, well, I was doing a physics demo and just laws of physics broke and it blew through my hand, sorry. Okay?
Next year, continue
No,
rolling.
shh. Okay. So it's not going to go back up. It's going to keep going down. Now, Alex, by virtue of the fact that it keeps going down, which is a horrible line, what's it doing once it crosses here? Speeding up or slowing
It's
down?
speeding up in the other direction.
Bingo! Now, what's going to make it speed up in the opposite direction?
That spring.
Yes, because Mother Nature doesn't like. She changes it back into kinetic energy. So at this point, here's what we've got. So we're like this. So we're slowing down, and then bam, we start to do what? Speed up. At this point, we've left the wall. So Sydney, at that point, what's the graph going to do?
The velocity is going to start heading back to 0 because it's going to have friction. It's going to start slowing it back down.
Bingo. So the line's going to do something like this, right? So I'm slowing down, speeding up, then, so it's the only time the cart speeds up,
When the spring starts expanding.
when the spring starts expanding. The rest of the time it's doing what?
slowing down.
So it's the only time velocity and acceleration have the same sign.
Spring is expanding.
When the spring is expanding. All the other times, velocity and acceleration have the opposite sign. Connor S. What's the sign of that slope, positive or negative?
Positive,
Why?
because acceleration's increasing.
Well, at least I have a positive acceleration.
That's that,
But I have a positive acceleration with what sign of the velocity?
negative,
Therefore, I
it's slowing down.
slowing down. Okay? Go with that. Now, let me hand out the letter. Stop that for a second. Andrew, please.